Hi there, welcome to the 30th episode of the Synth Project, where we are going to build a synth together. In our previous episode, we introduced the concept of the control voltage processor. This exciting module combines 4 unique elements that offer various ways to manipulate the control voltage sourced from any module within the synth. Additionally, it features a linear VU meter, complementing the capabilities of the existing oscilloscope in our synth rack. Today, we will go through the design and testing of the first control voltage processor unit, the DC mixer. So, without further ado, let's dive into this great and useful subject. As you may recall, the DC mixer is a device capable of combining control voltage signals from different sources, resulting in a more complex and versatile signal that can be used to control various modules within our synth. The DC mixer we are about to make features 3 individual inputs, each with its own level control. Additionally, we have an offset control that allows us to establish a minimum value for the output signal. In addition to the main output, we also have an inverted output. This inverted output provides an upside-down version of the signal present on the regular output. This additional control voltage can be incredibly useful when it comes to creating unique effects with our synth. Here is the schematic of our DC mixer. On the left side we have 3 CV inputs, each equipped with its own level control. At the bottom there is a 4th potentiometer that allows us to adjust a voltage ranging from 0V to plus 12V. All 4 potentiometer cursors are connected together each through a 1 MΩ resistors. This node is where the magic happens, as it enables the mixing of the input signals. Since the output voltage at this node is 1/3 of the sum of the 3 inputs, we feed it into an amplifier with a gain of 3, which utilizes one of the op-amps from the LM358 IC. As a result, the amplifier's output voltage is equal to the sum of the 3 input voltages. To introduce an additional DC component to the signal, we can manipulate the offset potentiometer, and this allows us to establish a minimum value for the output signal, depending on the position of the potentiometer RP4 cursor. Now, let's talk about the inverted output. We take the output of the amplifier and feed it into an inverting amplifier, which is created using the second op-amp of the LM358 IC. This op-amp is configured to function as an inverting amplifier with a gain of -1. Essentially, we need to add a negative signal of -10V to the input signal. And by combining these 2 signals, we achieve a resulting signal that ranges from -10V to 0V, depending on the value of the main output. The gain of -1 sets the output within a range of +10 to 0V. In simpler terms, this configuration provides an output signal equals to 10V minus the value of the main output. This setup ensures that when the main output is 0V, the inverted output is 10V, and when the main output is 10V, the inverted output is 0V. The same principle applies to all the voltage levels in between, and therefore as the main output increases, the inverted output decreases, and vice versa. Now, it's time to put our DC mixer circuit to the test in the lab and see if it truly delivers the functionality we desire. We will connect a control voltage source to the inputs and observe the output behavior. First, we will connect a control voltage signal to the inputs and adjust the level controls to vary the influence of each signal. By manipulating these controls, we can experiment with different combinations of control voltages and observe how they interact and blend together. Next, we will adjust the offset control to introduce a DC component to the output signal. and this will allow us to set a minimum value for the output voltage, which can be useful in defining the lower limit of control voltages for certain applications. Additionally, we will examine the inverted output and observe how it behaves in response to changes in the main output. As the main output increases, the inverted output should decrease, and vice versa. Throughout the testing process, we will monitor both outputs using an oscilloscope to ensure that the circuit is operating as expected and producing the desired results. Here is the DC mixer mounted on a large breadboard. I am using such a big breadboard so I can keep adding all the other elements of the CPU processor to it, keeping everything in the same place. At the bottom of this breadboard I attached a support to hold a set of 4 potentiometers, those for adjusting the level of the 3 inputs and the one to adjust the offset value. On this side I have added pins to connect to both outputs, the main one and inverted one, probes for the 2 channels of my oscilloscope. The probe on the left, which is associated with the yellow trace on the oscilloscope, is connected to the main output. The probe on the right, which is associated with the blue trace of the oscilloscope, is connected to the inverted output. Here you can see the actual circuit with the LM358 and all the other components wired together according to the schematic. The 3 inputs are connected to the 3 pins right here. I have connected the output of my function generator to 2 of the 3 pins, so we can pilot with the same signal 2 independent inputs. The function generator is set to emulate a control voltage that changes from 0 to plus 10 volts and vice versa periodically, basically a square wave. The frequency of such wave is set to 10 Hz, and you have also probably noticed that I have set an offset of 5 volts. That is because the actual function generator output would otherwise create a square wave that is 10 volts peak to peak, but that goes from minus 5 volts to plus 5 volts. The offset value of the generator changes the output to a signal that goes from 0 to 10 volts. And here is the oscilloscope where we can see the control voltage output in yellow and the inverted control voltage output in blue. Right now, all the potentiometers are set to a level of 0 volts input, and so the main output is at 0 volts, while the inverted output is at 10 volts, because the center line on the screen represents the 0 volts for the blue trace. And both channels are set to 5 volts per division. Let's now increase the level at one of the 2 inputs. Let me adjust the oscilloscope trigger so the traces are stable. See how we now have a main output that goes up at intervals and an inverted output that goes instead down from the plus 10 volts at the same times. And see when the main output increases, the inverted output decreases of the same amount. Here you can see the current position of the input levels. I have used both of them so far, and therefore the output is already a mix of the 2 input signals. Let me now lower both levels to the minimum. And now you can see that there is no signal at the output. I'm now moving only one input level to half the way. And now the main output is at 5 volts, as well as the inverted output, although this one comes down from above. And in fact, in this other interval, the main output is at 0 volts and the inverted is at 10 volts. Plus 10 volts. If I now increase the level of the other input signal, this should add up to the one already present, and we should see the traces change. And you can see that whenever the yellow trace goes up, the corresponding interval of the blue trace goes down. These other areas instead don't move, because there is no input signal in these intervals. Let me lower the input level a little bit, and let me show you what happens with the offset control. So far, the offset is set at 0, but as soon as I add it on top of the signals, I should bring up the whole yellow trace and simultaneously bring down the whole blue trace. And here, you see, that is exactly what is happening. I can increase and decrease the offset level, and both outputs are affected at the same time. And so, basically, the offset defines the minimum level of the main output and the maximum level of the inverted output. With its ability to combine and manipulate control voltage signals, the DC mixer opens up a lot of possibilities for controlling the sound of our synth. However, this is just the first step toward the completion of the CPU processor module. In fact, we still need to add to it a number of other units. Once everything is designed and tested, we will finally create the full module for our synth and install it, so we will be able to start using it. But this is the subject for the next few videos of the Synth Project. For now, let me just remind you to subscribe to the channel and activate the notifications for new videos if you haven't done so already. This way, you will not stay behind with the evolution of this great project. See you soon in the next video, and as usual, happy experiments!